This is Group 16 checking in for our final video presentation. One team, one dream. I'm Greg Harold.
I'm Kyle Wagner.
And I'm Alex Bang. Our project started with our sponsor coming to us, looking at different ways that we could implement our project in a UAV. Our option that we ended up going with was a navigation system that the UAV could theoretically implement when it's navigating around.
After doing many months of research on different navigation systems, we finally chose to go with a single GPS unit. The single GPS unit, combined with other components, help fulfill our project, which is a GPS navigation model. Now we will walk you through a block diagram which will help you better understand our project. This is the GPS navigation model block diagram. As you can see, we have a power supply which supports power to all of our various components. We have an ultrasonic rangefinder, a GPS chip, an accelerometer. All of this is interfaced using the Atmega 128 microcontroller. All of the outputs that we need to be displayed are displayed through the LCD from the Atmega. We have code written to help the Atmega interface all these components, and it is all supported inside of a case. So moving on, we have our power supply. Our power supply consists of 8 AA rechargeable batteries that output a total of 12 volts. We use 2 buck regulators to step down the voltage to 3.3 volts to help supply the ultrasonic rangefinder, the GPS, and the accelerometer's power. And then 5 volts going to the Atmega 128. The ultrasonic rangefinder allows recognition of height, so it tells us how high off the ground our system is while it's operating. It integrates with the Atmega using analog, and it's 3.2 millivolts per 1 centimeter. Next slide is the GPS chip. The GPS chip sends a UART signal into the Atmega 128, which contains an NMEA message. This message tells the device its latitude, longitude, and true heading. Using code, it also tells us many more things, but using code, we can pick out these 3 sets of information which we are using. The accelerometer allows us to determine the pitch and roll of our system. This is very useful for making sure that our system remains level at all times of operation. The Atmega 128 is the heart and soul of our project. It takes in all the information from all the components and stores it and displays it so that we can tell where we are and where we're going. The case is a simple metal case, but very, very necessary. It makes sure that people don't mess with the wiring, and so nothing can come loose or electrocute somebody. We had to make sure that it had a top that was easily able to be taken off. This made sure that we were able to take off the case and plug in the Atmega so that we could reprogram it and put in fresh targets for every time we wanted to use it.
Having little experience with C coding, and especially C coding in microcontrollers, the code block was one of the biggest challenges for us as a group. We went through various phases to get our code working. Initially, all we had to do was just be able to write anything we could on the LCD screen. This took a while, but we eventually figured it out. Because so many of our devices also output an analog signal, the next big one was using the A to DC converter, or analog to digital converter, on the Atmega. We had to figure out the coding for this, and then from that, how to display it correctly onto the LCD. After we had figured all this out, we then went on to the GPS. Initially, we struggled with just reading any signal that was in the USART format, or the UART format. Once we could read anything from this and just get some data, this is when we really utilized the code to pick just the pieces that we wanted out. As Kyle said earlier, the only thing we picked out was the latitude, longitude, and true heading. From this, we would get a GPS update about once every second. Once we had our update, we had to do trig functions to find the distance between our current point and our target point, as well as the angle between the two of them. So here is the actual components to our navigation system. As you can see, it's made up of a bunch of different things that are kind of around in different places. So we'll try to go over them and explain why they are at their certain positions. To start off, we have our battery pack here. As you can tell, there's 4 AA batteries on this side, and there's also 4 on the other side. So these are rechargeable batteries, and we take them out whenever we have to charge them if they're getting low. Come around here, you can see our buck converters. We have one rail that's a 3.3, and then one rail that's a 5 volt. For this, we bring the batteries or the power in from the batteries here, and it goes through it, and then we output either through this USB to power our Mega, or we have a bunch of different 3.3 rails that they power all of our other components, such as the accelerometer and GPS. Going over the GPS, as I just said, it draws its power. The red blinking light means that it's currently getting a signal from a GPS satellite. If it's just red, it means that it is on, but it does not receive a signal. From here, it has its GPS out in the UART format that plugs into that Mega. And also the antenna to the GPS is right outside it, right next to the LCD, which displays the different values that we are reading out. Next, we have the accelerometer and also the ultrasonic rangefinder. The ultrasonic rangefinder is put here because it needs an outside facing edge so it can get the laser reading from the height. So same thing, we have a 3.3 rail that connects to our converter, and then this has an analog output that goes into our port F, which is the ADC port of that Mega. Next is the accelerometer. The accelerometer is faced and placed on this wall because our normal position of the navigation system is like this, so it needs to be on a flat surface, hence why it is on this back wall. So this again gets its power from the converters, and then it has two outputs, one for the X and then one for the Y, which correlate with our pitch and our roll. Once again, those go to the ADC port or analog digital converter port of our Mega, which is at port F. As you can see here too, we have to tie one of the pins of the accelerometer high to enable the accelerometer to continuously read values. Just a couple other things real quick. Here's our LCD port that goes from our Mega out to our LCD. It has male and female headers, so they're easily removed. We have our programmer here that goes into our Mega. If we need to, we can disconnect the power from here and connect it into a programmer to program that Mega directly from the computer.
Here's a list of our engineering requirements that were met during our project. The first one has to do with interface learning, this being teaching someone how to enter GPS coordinates into our system within 30 minutes of training or less. This essentially entails entering in a latitude and longitude coordinate into our code. Next, we have the power supply. It needs to be able to maintain power so that all of our components can function for at least 60 minutes in use, all simultaneously. Next, we have the system must be able to operate at a distance of between 5 and 20 feet from the ground. Using an ultrasonic rangefinder, we're able to determine how far away we are from the ground and display this value on the LCD using the ultrasonic rangefinder. Next, the total system must cost $600 or less. This is the budget that was provided from us, from our sponsor Voxel, and from Oregon State University. Next, the navigational model must be able to recognize when it is within 10 meters of any given target. This was utilized using the GPS and would display on the LCD when we are close to a target. Also, we must be able to have at least 5 targets programmed into the GPS system at one time. When all the targets are programmed in, we will be able to travel to them and see that we have reached each target one after the next. This also has part to do with our requirement of successfully navigating to 5 targets. Once one target is reached, without having to do more than one additional pass-through, the next target must be navigated to as well. And finally, the system as a whole must weigh no more than 1 kilogram.
After walking 100 meters away, which will be displayed by our thing, we will now walk towards the destination and show that it says target reach when we're within 10 meters. Walking. We will periodically read out how far away we are. Walking. We're now under 100 meters. Our target is Greg over there in the orange. We're now under 60 meters away. I'm gonna hold it so you can see. Okay. walk slowly so we can just kind of. And we've already reached our next target, which is displayed by the new set of coordinates. Oh, and you can see that we are 10 meters away. Well, within 10 meters, this is 25 feet, and Alex is less than that, 25 feet.
So here we have the ultrasonic rangefinder just sitting about 4 feet off of the ground, giving us pretty steady reading. And we're going to go ahead and just walk forward with it, kind of just head towards the other side of the room, and make sure that the ultrasonic rangefinder actually maintains that distance as we're moving forward. So now just looking at the pitch and roll angles as they cycle through, you'll see that they're relatively stable because our system is in its upright and essentially neutral position. So once the rangefinder cycles back to the LCD, we'll start moving forward with it and taking a look at those values. So now the rangefinder is moving, and we're just kind of slowly walking forward here and making sure that value stays relatively the same as we move forward, and it seems to stay pretty steady. And now we're back to the pitch and roll, and they stay steady as well. So now we're looking at the pitch and roll angles and how their measurements work out to the actual angle of the system. So looking at the pitch right now, it's at a maximum as it's completely on its side. And the roll right now is still steady because that's the forward and backward movement of the system. And so that's sitting pretty close to zero as well. And right now it's blank, displaying nothing on the screen because we're not actually receiving a signal from the GPS as we are inside. But we're moving back to the ultrasonic rangefinder reading that displays. And so when we set the system up completely upright, we've got about a 0-degree reading on the pitch angle, which should also be found in the roll as well. But moving it down to about a 45-degree angle, you'll note that the system is sort of close to 45, but in actuality does not get the correct measurement. There were two engineering requirements that we did not meet for our project. The first had to do with the system attitude, that being the pitch and roll of the system while in motion. We did not account for gravity when we were measuring our pitch and roll, and this led to values that were not linear. And so when we measured initially, we only checked the minimum and maximums, those being 0 and 90 degrees. Those worked out fine, but intermediate values did not end up being the same. It's important to note that in a given range, your scale may not always be linear. And even if it is supposed to be linear, it may be slightly skewed from your expected values. The second engineering requirement that we did not meet was a trajectory angle. Initially, we used the true heading from the GPS to try to give us an angle between us and our target. This was found using the direction that we were traveling, but the speed that we were traveling at was insufficient to get a solid angle, and so we ended up getting skewed results. In the future, a group could most likely use a digital compass to get a more accurate reading, but this would increase system cost and weight that were two things that we were very strictly trying to keep down during our testing and design process.
These are our recommendations for future students. The first recommendation that we have is to communicate with your sponsor frequently, especially during the fall term. This will make sure that you and your sponsor are on the same wavelength and that you both know what needs to be accomplished through the class and what is outside of the scope. The next recommendation that we have is to set a schedule early and to make sure that you guys continue to meet up frequently. Setting a schedule will make sure that you and your group partners all understand what needs to be done, and it'll get you in the routine of meeting up and hopefully reduce slacking off. Lastly, one of our biggest recommendations is to pick a project that you are interested in and will enjoy. You're going to be spending the whole year working on this project, so you might as well find something that you are passionate about and that you will enjoy working on instead of slaving away in the lab for 3 terms and not enjoying it. So have fun. Group 16, One Team, One Dream, we'd like to thank you for watching our final presentation video.
A big thank you goes out to Dawn and our sponsor Voxtel for all the help and support that they did throughout our project.
And last but not least, a big thank you and what up to Ria for being the greatest Scrum Master of all time. Thanks again.